All right, today we're going to talk about applying integration, which is what we talked about in the last chapter. We're going to apply it in a few different situations. The one topic that probably needs to be discussed first is the area between curves. So rather than just finding the area underneath a curve, now we have two curves and we're finding the area between them. All right, so as an example, I want to find the area between y equals the square root of x and y equals x squared. So here's a graph of what they look like, and you should probably start out there because there's some things that you can really only figure out visually by looking at the graphs. First of all, we can see that the graphs cross at 0, 0, and 1, 1. So this region right in here is what I'm trying to find the area of. Also, when I look at that region, it's important to figure out which function is on top and which function is on the bottom. And this red curve, which is obviously the square root of x curve, that's the one on top. And then the x squared curve is on the bottom. So basically what I'm doing is I'm taking the area underneath the square root curve, which would go all the way down to the x-axis, and then I'm going to subtract off the area under the x squared curve, and that's going to leave me with the area between them. So that's why it's important to figure out which curve is on top and which one's on the bottom, because you do need to subtract them in the right order. Otherwise you might get a negative answer. So in my integral, I'm starting at an x value of 0, ending at an x value of 1. My upper curve, my upper y is x to the 1/2, and my lower y is x squared. Okay, so here's how I set it up. I put my a and b on top and bottom of the antiderivative sign, that funky s, and then I do my upper y minus my lower y. All right, so as I said, I'm going from 0 to 1. So there's my a and b. X to the 1/2 is on top, it's my upper y, and then x squared is on the bottom, it's my lower y. So if I take the antiderivative of x to the 1/2, that's x to the 3/2 over 3/2. And if I take the antiderivative of x squared, that's x cubed over 3. Now all I need to do is evaluate that at 1 and 0 and subtract the results. So first I simplified it, changing the division by 3/2 into multiplication by 2/3. Okay, so if I plug in 1, I get 2/3 minus 1/3, and if I plug in 0, I get 0 minus 0, so the total area is 1/3. All right, sometimes you might get something like this. Find the total area of the regions between the x-axis and the graph of y equals x cubed minus 6x, or minus x squared minus 6x. So here's what the graph looks like. The red line is just kind of emphasizing where the x-axis is, but I want you to realize that I can't just take the antiderivative of this function, because sometimes the curve is above the x-axis and sometimes it's below. Anytime the curve is above the x-axis, you will get a positive area, but anytime it's below, you will get a negative area. And we want to avoid that because I want to find the actual area. I don't want to take the positive of this area and the negative of this area and combine them together. I want the positive of this area and the positive of this area. So what I need to do is look at where it is above the x-axis and where it's below. So from x equals -2 to x equals 0, the curve is above, and then from 0 to 3, the curve is below the x-axis. So I actually need two integrals. The first one, from -2 to 0, is going to have the function minus y equals 0, because the curve is on top and y equals 0 is on the bottom. Then from 0 to 3, 0 is on top, and I subtract the function. And notice that I changed all the signs of all the terms just to make it easier on myself. Okay? If I integrate the first function, I get 1/4 x to the 4th minus 1/3 x to the 3rd minus 3x squared. Notice that in the second one, I get exactly the opposite. So all the pluses have become minuses, and all the minuses have become pluses. So I could have just as easily figured out what that integral was and then changed the sign of it, but I'm essentially doing the same thing here. Plugging in 0 into this gives me 0. Plugging in 2 gives me all of this. Plugging in 3 into this antiderivative gives me this, and plugging in 0 gives me 0. So it's just a matter of adding a bunch of fractions and numbers, and that gets me 253 over 12. The only weird thing that can happen is instead of being asked to find the area between two x's, you'll notice that this is the area here that I'm asked to find the total area of. So what I have to do then is, since I'm starting at a specific y and ending at a specific y, then what I need to do is, instead of having my functions be expressed as y equals something in terms of x, it has to be x in terms of y. So the first function, which was y equals x cubed, now becomes x equals y to the 1/3. And the second function, this y equals 5x, becomes x equals 1/5 y, or 0.2 y. All right, and now I just treat it like I would, but now everything's in terms of y instead of x. So what I have is the antiderivative from 1 to 4. If you look at what's on top, this curve, this x equals y to the 1/3, that's kind of on top, meaning it's further to the right if you tilt your head. And then the 1/5 y is on the bottom, or it's actually further to the left, or you can again tilt your head to see which one's on top and which one's on bottom. So my antiderivative of y to the 1/3 minus 0.2 y is 3/4 y to the 4/3 minus 0.1 y squared, and all of that calculation gives me 2.5122. And that's the lesson. So if you have any questions, please let me know, and I will see you tomorrow.